Let's discuss basic principle of transformers. So as we discuss transformers, we have two coils separated by some dielectric. These two coils either are wrapped on iron core or an air core. One more thing that I should mention that I did not mention earlier is the placement of these two dots. What these two dots represent is the sides on the primary side and the secondary side are uh, that are in phase with each other. So for example, if the dot is on top on the primary side and on top of the secondary side, that means this side is in phase with this side. That means the top side of the primary is in phase with the top side of the secondary. If this dot, which is on top of the secondary, we move it to the bottom of the secondary, that means the top of the primary side, voltage on the top of the primary side will be in phase with the voltage at the bottom of the secondary side. So remember, the two dots represent the sides, the voltages that are in phase with each other on the primary side and the secondary side. Okay, so we discussed that earlier. Actually, we solved a problem based on this, that the magnetomotive force that will be produced by the primary coil and the secondary coil, basically you can calculate those magnetomotive force as N1 times the current that is running in the primary coil and N2 times the current that is running in the secondary coil. And these two magnetomotive forces are equal because the same flux is linked with both primary and the secondary sides. So the voltage induced in the primary side, the RMS value of that voltage, can be calculated as 4.44 F number of turns on the primary side and the flux that is linked with the primary side, which is we're calling it phi p. And the same flux linked with the secondary side, peak value of flux, and we are calculating the RMS value of the secondary side, similarly 4.44 F N2, because of course number of turns on the secondary side are different than number of turns on the primary side, N2 phi p. And based on if N1 is greater than N2 or less than N2, your E1 will be either greater than E2 or less than E2. If E1 is greater than E2, it is called a step down transformer, and if E1 is less than E2, it is called a step up transformer. Now if we take the ratio of E1 and E2, then what you're going to get, 4.44 F and phi p will be cancelled each other, and you are going to get N1 over N2. So the ratio of the RMS voltage or the peak voltage between the primary and the secondary side is the turn ratio. This is called the turn ratio, and it is generally represented by lowercase a. So E1 over E2 is N1 over N2, and that's the basic relationship of transformers, so make sure you remember that. Here I'm explaining the dots on the primary and secondary side. A step up transformer and a step down transformer. If N1 is greater than N2, it is a step down transformer. If N2 is greater than N1 or N1 is less than N2, then it is a step up transformer. Okay, let's look at 9.4. That is when you connect a load on the secondary side. So when you connect a load on the secondary side, of course you have current in the primary side. Even if you don't have any load over here, you still have some current in the primary side. Once you put the load on the secondary side, then the current starts flowing on the secondary side as well. Now we discussed that the flux is mutual, hence the MMF produced by the primary and secondary are same. So if we equate that MMF, N1 times I1 and 2 times I2, then we can take the ratio, or we can take the ratio of I1 over I2, which will be equal to N2 over N1, which is 1 over turn ratio. So this is another important relationship between the primary current and the secondary current of the transformer. That is, the ratio of the primary to secondary current is 1 over turn ratio. This is another basic relationship that you need to remember. Now, another extremely important relationship or any extremely important property of transformer is whatever voltage, whatever apparent power you have on the primary side, it is going to be the same on the secondary side. So we can write E1 over E2, which is equal to N1 over N2, and N1 over N2 is equal to I2 over I1. So we replace that N1 over N2 by I2 over I1. So if we cross multiply E1 times I1 and E2 times I2, that means E1 I1 apparent power on the primary side is equal to apparent power on the secondary side. And this is an extremely important property of transformer, that is, they do not change the power transfer from the primary to the secondary side. Apparent power transfer from the primary to the secondary side. So in other words, if you have E1 larger than E2, then of course I1 will be smaller than I2, because again these two are equal to each other. The product of E and I is equal to each other. So anytime you have primary voltage greater than secondary voltage, your primary current will be less than the secondary current, and vice versa. Now when you connect a load on the secondary side, you can calculate the load as the ratio between E2 and I2 using Ohm's law. So when you put E2 over I2, okay, let's go back. The load that source sees, so you have an actual load connected on the secondary side, which is this load. But when the source is supplying the current, basically it is supplying the current to some load. Now the load that source sees can be calculated as the ratio between the source voltage and the current that it is providing, which is I1, primary current. Now ES and E1 are equal. If you do not have any line impedance, then ES and E1 are equal. So far that's what we are assuming. So Z1 is equal to E1 over I1, and then we can go ahead and plug E1, which is turn ratio times E2, and I1, which is I2 over turn ratio. So we're gonna get A square, that is the turn ratio square, E2 over I2, and E2 over I2 is the impedance connected on the secondary side, or load on the secondary side. So that means the load that source sees is equal to A square, turn ratio square, times the actual load that is connected on the secondary side. And this is an extremely important ratio, or extremely important property, because as I mentioned in the first lecture, if you have some load that you want to connect, but you don't have the actual value of the load, but if you can tweak the turn ratio of the transformer, then even though you don't have the actual value of the load, but if you can make A square times the value to be equal to what you are planning to connect, then you can still achieve your goal. So in this way, whatever the load that is connected, the source does not see that load. What source sees is that load value times the turn ratio squared. That's what source sees. So many times it is quite convenient for us to have a transformer and some load that we do not have, then we can connect some other load such that the transformer turn ratio times that load equals to the load that we actually want to connect to the transformer. So this is called, in the next topic, which is impedance shift, we're gonna see that how we're gonna make use of this property. Z1 is equal to A square times Z2, that is primary load, is equal to A square times the load that is connected on secondary. How we can make use of this property to shift the actual values of the load and the resistance and inductors on the secondary side to the primary side, and from primary side to the secondary side.